When you picture a volcano, you probably see that classic cone-shaped mountain, right? Maybe with a little smoke puffing out the top. But that image, that's just the tip of the iceberg. Today, we're going to peel back the layers of rock and fire to show you the complex, wild engine that drives one of the most powerful forces on our planet.
So let's just start by blowing up the biggest myth right away. We call them mountains, we think of them as mountains, but what if they're not? What if their entire origin story is something else completely?
Think about it like this. A regular mountain, say, in the Himalayas, gets formed when tectonic plates slam into each other, crunching up and pushing rock that's already there. They're basically carved out of the existing crust. A volcano? No way. A volcano builds itself from scratch. It's a constructive process, piling layer after layer of its own lava and ash, literally growing from the inside out.
So if it's not just a mountain with a hole in it, what are we really talking about? Well, to get what's happening beneath the surface, we have to throw out the old textbook drawings and look at a whole new model. First things first, forget the cartoon image of a giant bubbling lake of lava just sitting underground. That's not really how it works. Modern science has a much cooler name for it, a trans-crustal magmatic system. The keywords there are trans-crustal and system. This isn't one simple pool. It's a huge, interconnected network that can snake its way for kilometers up through the Earth's crust. And this is where the science has really changed. We've gone from that old vat of lava idea to what geologists now call a crystal mush. Instead of a big pool of liquid, imagine a semi-solid slush. It's mostly a framework of solid crystals with a little bit of liquid melt trapped in between the gaps. The actual magma that can erupt is only the stuff that gets squeezed out of this mush, kind of like wringing water from a sponge, and it only happens right before an eruption.
So what does this engine, this whole plumbing system actually look like? Let's break down the key parts that make it all work.
You've got the conduit, which is the main highway for magma trying to get to the surface. But it's not always a straight shot up. Magma can force its way into cracks in the surrounding rock, forming what we call dikes and sills. Dikes are these vertical sheets of magma that actually act like the structural ribs of the volcano, making it stronger. Sills are when magma spreads out horizontally. And all of this plumbing, one way or another, leads to the vent. That's the surface opening, where the fireworks happen. Okay, we've got the structure down. Now let's talk about the fuel itself, the magma. Because not all magma is the same. In fact, its chemical personality determines literally everything about how a volcano is going to behave. And believe it or not, it all comes down to one key ingredient, silica. The percentage of this one compound is the master control knob that decides whether an eruption is a gentle, slow-moving flow or a catastrophic, mountain-shattering explosion. Here's how it works. Magma with low silica, like basalt, is runny and fluid. Think warm maple syrup. Gases can escape from it easily, so you get those gentle lava flows like you see in Hawaii. But as you crank up the silica content, the magma gets thicker and stickier and way more viscous. The thickest stuff, rhyolite, is so sticky it acts like a giant plug in a bottle, trapping all the volcanic gases and building up insane amounts of pressure. Okay, that sounds super technical, I know, but here's all it really means. On a microscopic level, those silica molecules start linking together, forming these long, tangled chains. And those chains just do not want to move. It's the difference between trying to blow bubbles in water versus trying to blow bubbles in thick, cold honey. In the honey, the bubbles get trapped, they merge, the pressure builds and builds and builds until the whole thing just detonates in a massive, violent eruption. Now, this is all fascinating stuff, but it brings up a huge question. All of this action is happening deep underground, hidden beneath kilometers of solid rock. How in the world could we possibly know any of this is true? And for most of human history, we didn't. The inside of a volcano was a complete black box. It was total speculation. We could see what came out at the top, but the engine driving it all, a complete mystery. The challenge was just immense. So how do you peer inside a mountain of solid rock? How do scientists actually get a picture of this hidden world? Well, the answer, amazingly enough, comes to us from outer space. It's this incredible technology called muon tomography. And you can basically think of it as giving a volcano a CT scan, but using cosmic rays. See, muons are these tiny subatomic particles that are created when cosmic rays from deep space slam into our atmosphere. They are constantly raining down on us, and they're so powerful they can punch through kilometers of rock. The way it works is genius.
Scientists set up special detectors to count how many of these muons make it all the way through the volcano. Dense, solid rock will absorb more muons, while less dense areas, like a magma conduit or a pocket of gas, will let more of them pass through. And by doing this, you can create a high-definition density map of the volcano's guts with up to 10 times the resolution of older methods. We've gone from a blurry, grainy image to a crystal-clear scan.
And this isn't some sci-fi future tech. It's happening right now. At Mount Asama in Japan, it helped map out the hidden plumbing. At Vesuvius, they're using it to map the dangerous lava plug in the crater to figure out how it might erupt next. And at La Soufriere volcano, scientists were able to watch density changes happening inside the volcano in real time. That is a massive breakthrough for forecasting eruptions and ultimately for keeping people safe.
All right, so we've journeyed through the rock, through the fire, but there's one last secret hiding inside volcanoes. And honestly, this one might be the most surprising of all. It turns out they're not just forces of destruction, they can also be cradles for life.
I want you to meet the Extremophiles. These are microbes that don't just tolerate extreme conditions, they actively thrive in them. We're talking about environments that would be instantly lethal to almost any other life form we know. Crushing pressures, temperatures well above boiling, and water as acidic as battery acid.
Deep inside these volcanic systems, in total darkness, life has found a way. Since there's no sunlight for photosynthesis, these microbes have evolved to use chemosynthesis. They literally eat the chemicals coming from the volcanic rock and gases, things like sulfur, iron, and hydrogen, to power their lives. This is a completely separate food web, a whole hidden biosphere running on geothermal energy right beneath our feet. And this is where it gets really mind-bending. These lava tubes and volcanic vents on Earth, which are home to our planet's toughest life forms, they are our best guess for where we might find life on Mars. If life ever got started on the red planet, it probably retreated into underground caves and lava tubes just like these to escape the harsh radiation on the surface. So studying these extremophiles here is literally teaching us how to search for aliens out there.
So in the end, a volcano isn't just a mountain. It's a self-building geological engine. It's a chemical reactor whose personality is decided by a single ingredient. We can X-ray its heart with particles from space, and deep inside it hosts a hidden biosphere that could be a blueprint for life on other worlds. It really makes you wonder, doesn't it? What other incredible secrets are just waiting to be discovered right beneath our feet?